and do that. So what we were doing, what is this? I don't want to play these. We talked last time, but we didn't make much progress to that. We made it basically this fair. If you have some money in some account that has some interest rate, with some interest rate R, where R is presumably a number that's reasonably close to zero, you would measure it on the order of like 3% is a pretty good interest rate. Compounded annually, then what do you wind up with? The amount after some amount of time is the principal, the initial money you put into the account, times 1 plus that interest rate, raised to the t, where t is measured in the number of years you put in. Cool. But a lot of times you'll have accounts that compound more often than just once per year. Like maybe you have something that's compounded quarterly. Then what do you do? Well, just like we saw down there, you act like you've divided the interest rate by 4 because you want to apply it 4 times per year, and the philosophy is, doing a quarter of something 4 times per year, that's kind of like just doing it once over the full year. And that P is just a number, it's the initial investment. So you act like the interest rate is 1 quarter what it used to be, but you need to apply that interest not once per year, but 4 times per year. So instead of that being t, which just counts the number of years, I guess now it's 40. That agrees with what we did last time, I think. And in fact, there's nothing special about the number 4. Here is the general formula. If you have some initial investment, P in principal, in an account with annual interest rate R, where, for emphasis, that word annual is important there. I mean, it could be like a weekly interest rate, and then just time would be measured in weeks instead of years. Which is compounded n times per year, then the amount in this account after t years is given by, well, you act like you had an interest rate of n divided by r, because you want to apply it n times. Start with the initial interest and then multiply it by 1 plus what that interest rate would be, but do it n times t times. Fair enough? So let's make some quick comparisons. So let's suppose you put 150 in an account. So there's the initial investment, the principal, with an annual interest rate of 5%. And let's vary how often it's compounded. So if you compound this monthly, so there are 12 months per year, so 12 times per year, then what's the formula for how much money will be in there after 10 years? Well, what's the initial investment? 150. $150 multiplied by 1 plus, what's the interest rate? 0.05, because it's 5%, and percent literally means per 100, so 5 divided by 100. How many times am I compounding it per year? 12 times. And now I raise it to n times t. What's n times t in this problem? Say louder. 12 is n times t is 10. Oh, neato. That's definitely not something that I would want to compute directly by hand. Raising something to the 120th power by hand is hard. So if we want to see what this is about, I guess this is an occasion to resort to machine. And I mean, like, enough people are pulling out their calculators that I feel like by the time I do the computation, someone will have it done already. So I kind of don't want to. What is that about? 247.05. And I guess this is in dollars. Nice. So that's nice. That's somewhat on investment. A 5% interest rate is kind of unspeakably high. You wouldn't expect something that high really ever. If someone's promising you a 5% return on investment without risk, they're probably stealing your money. Well, let's see what happens if you vary this a little bit. Let's say you compound it daily, where here I'm going to imagine there's no such thing as leap year, so 365 times per year. Let's just see how that varies. You'll write down your own thing. So A at 10 years will be something looking pretty similar. 150 times 1 plus 0.05 for a 5% interest rate divided by 365 times per year, raised to the 365 multiplied by 10. And I'll pause for a moment. What are we seeing? And maybe I'll round everything to the penny because that's the way money is often treated. Is it a zero with you?
It is a zero.
Okay, excellent. Nice. So, which of those is the better return on investment? The second one by 25 cents over 10 years. Let's vary this. So, what I'm going to think about now is what happens if you let that number of times you compound the interest get really, really, really big. So let's check it 10,000 times, 100,000 times, and 1 million times per year. And I think I'll do one, I'll have half of you do one, and half of you do the other. Maybe I'll do the million. 10,000, 100,000. So running it for n equals 1 million. Isn't 10 to the 9th, is it? So, excellent. That sound has gone away quickly this time. $347.30.82, where I've gotten those extra couple of digits so that hopefully we can actually detect the difference between some of these. When n is 10,000, what'd you get?
I got 247.308.
Okay. Anyone good more digits than that? I know I often don't care about this sort of thing. Yeah.
I got 3081.
Okay, a noticeable difference at that many digits. What about when you plugged in 100,000? $157? I think I'd be absolutely atrocious if I had the responsibility of taking down numbers like that regularly. Yeah.
I got it.
Oh, okay. Oh, even better, so we can really detect the number. All right, so looking at these numbers, let's just think about what happened. 247.05, 247.40, 247.30.30, 78. That number, what sort of pattern do you see, at least amongst these? Each time it does go up, but as n gets big, the amount it goes up gets smaller and smaller. Same observation. So do you think if I went to like a billion, the number would change much from this? Yeah. So these numbers are like stabilizing. So which is best? So like technically n equals a million is the better option, but not by much. What happens when n is really big? It seems to change less and less. So it's changing by less and less. It seems to be getting close to a single fixed number. And that single fixed number, I guess we can detect some of the digits. It's 347.3008. Probably 2 is the next digit, even if we went on to like 100 billion as our number of times we subdivide per year. So with that in mind, here is what happens in what's called the limit as n gets really big. You get continuously compounding interest. If you put a principal into a continuously compounding interest-bearing account with interest rate r for t years, you will wind up with the natural exponential showing up. And right now, that'll just seem like magic, right? And I'm not going to explain why in much detail. And somehow Euler's number is the number that's defined to make this happen. We'll check that this happens then. So let's take this exact thing. So if we have an initial investment of 150, an interest rate of 5%, and time equals 10 years, and plug that into this formula, what do you wind up with? Well, let's do it. So the initial investment is 150 times Euler's number raised to the R is 5%, 0.05. Times 10 years. That look pretty close to the numbers we were getting? Yeah. Group. So here's the fancy fact. If you compound more and more times, you'll just get close to this continuously compounding result. How's that feel? Pretty okay? Nice. So that's the last thing that I want to do with exponentials. I know there's one last example on that back page, but I think I want to not do that in interest of starting up this new thing. Everyone get a copy of the notes that I handed out at the start? Excellent. So, the topic that will occupy us for the remainder of the semester is trigonometry. And, well, like I get that a lot of people when they take this class have somehow seen versions of this material at points in the past. So maybe I'll see how people feel. How many people have learned some trigonometry at some point in the past? Okay. That was higher than I was expecting. How many people would even say they're reasonably comfortable with what trigonometry is? Okay. Well, let's start building the foundation of trigonometry here. So what are the trig functions based on? And, well, here's what they're based on. Here's the definitions of the trigonometric functions. Start at the center of the unit circle. So center at 0, 0, radius is 1, and you'll start right there at the point 1, 0 on the unit circle. Next, rotate about the origin some angle theta. You'll end at some point x comma y. All the trig functions do are record the coordinates at that point. Cosine of theta is the x coordinate. Sine theta is the y coordinate. And maybe we'll just do this quick sanity check. I wrote that down as if they're functions. Are they actually functions? Let's see, what does it mean to be a function? A function is a thing so that when I give you an input, when I give you an angle, the output is defined. It can't be two different things. If you start at 1, 0 and rotate forward by some fixed angle, do you always end at the same x coordinate? Yeah, so I think this is actually a function. They're both actually functions, which is good. So that's all I'm going to say about trig functions, the trig functions today. I want to focus on that wad. All right, we want to associate a number with an angle somehow. I want to know how to measure it. And there's one way that you already know. And let's see, did I think to bring it? No. Namely, thinking in terms of degrees. So let's do a quick overview of that. So let's suppose that someone talks about an angle of 1 degree. What do they mean by that angle? And, well, this is a vague question, and in some sense you already know the answer, but give me something. What is a 1 degree angle? Yeah, it's like a really small acute angle.
Yes. 1/360th of a revolution.
Yeah, 1/360th of all the way around the circle. And why is that? Well, how are degrees defined? Degrees are defined so that all the way around the circle is 360 degrees. So 1 degree is 1/360th of a full revolution. And as you pointed out, I know it says there to put a 90-degree angle. I don't know. There's my attempt at drawing something that might passably be a 1 degree angle. Similarly, if 1 degree is 1/360th of a full revolution, then what should 90 degrees be? A quarter of a full revolution, because you can simplify a fraction. 90 over 360 full revolutions. And 90 over 360, does that look like a fraction that simplifies? Yeah, there's the most obvious thing that you can cancel first, right? You can always move the decimal places over by 1. That's the same as dividing numerator and denominator by 10. So you have 9 over 360. Is 9 a factor of 360? Yeah, 9 goes into 360 4 times. So that's 1/4 of a revolution. So 90 degrees is a quarter of the way around the circle. That's a quarter of the way around the circle. That's a 90-degree angle. It's a right angle. But you already knew that, right? Here's the point. If you have an angle in degrees, all that you've thought of is dividing the full circle up into 360 equally sized pieces. And if 360 seems like a randomly chosen number, that only makes sense because you've always measured it that way. That's exactly the case. The only reason we use 360 degrees to break the circle up into is because the Babylonians did it. And the Babylonians did it because they liked the number 6. Same way we like the number 10. If this philosophy were used more recently, I guess probably like 400 would be the most natural thing to break it into, because it's nice to have like a whole number for 90 degrees. So that's totally non-natural. It's an arbitrary choice. I'm going to present a more mathematically rigorous way to talk about angle measure, and it'll be totally geometric. There won't be an arbitrary choice made. So here's the definition of the radian measure of an angle. So stand on a circle of radius r. Walk counterclockwise until you've covered a distance of s. So start on a circle. The radius is r. Oh, yeah, thank you. That is a perfectly drawn circle. I won't have you tell me otherwise. Walk forward on that circle until you've traced out a length of s. Well, hey, that traces out some angle down there, right? The radian measure of that angle is the arc length you've covered divided by the radius. So that's all radian measure is. Radian measure says if you want to measure the length of an angle, draw that angle in a circle, measure the length of that arc, divide by the length of the radius. And notice, there's no like arbitrary choice made. Measuring distances is something that you often want to do. There is now a definition of the measure of an angle, which is in some sense objective. So let's measure some angles using this. So this angle, the arc length is 2 centimeters, the radius is 2 centimeters. What is the radian measure of that angle? 1. Right, it would be 2 centimeters divided by 2 centimeters equals 1. So here's one thing to notice. Like there are units of distance next to the things in the numerator and denominator, and they cancel. The radian measure is a unitless quantity. There's not really a unit next to it. You say it's measured in radians to say that you measure the angle this way. Yeah?
So that would be like a 90 degree angle.
This would not be a 90 degree angle. This picture, I know I often don't draw my pictures to scale. This is to a consistent scale. This is about what 1 degree is. 1 radian is. What we'll see on the next page is how to convert between degrees and radians, and then we'll figure out how big a right angle should be. In fact, should we figure out what a right angle is right now? I think let's do that. Let's figure out how big a right angle is. So, aside, right angle. So, there's a circle, there's a right angle, and I'd like to know that angle measurement. Let's go ahead and put this in a circle of radius 1 just for convenience sake. So I want to know how far around that green arc is if I want to know the radian measurement. So that looks like it's a quarter of the way around the full circle. What's the circumference of the circle equal to? Yeah. 2 pi r. So this is a circle of radius 1. So the total circumference is equal to 2 pi times 1. How much of that does this angle take up? A quarter of it? Say again? Yeah, so I'll divide that by 2. It'll be an angle, this length will be pi over 2. Because that's 2 pi divided by 4. Oh, nice. Is that enough information to compute the radian measure of this angle? Yeah. Yeah, I mean, that's it, right? It'll be pi over 2 divided by 1. So a right angle is an angle of measure pi over 2. Useful? Excellent. So if you want to measure any angle, you can do exactly this. Figure out what the arc length is, figure out what the radius is. If you can pick the radius, then you may as well pick it to be radius 1, make things easier on yourself, and compute that ratio. Folks feel pretty good? Nice. So, there are two ways we have of measuring angles. We have degree measure, which is somehow arbitrary. Breaking a full circle up into 360 pieces is a weird choice to make. I guess it's nice in that the degree measures of angles that you encounter in your daily life will be like normal-ish numbers. They'll be somewhere between 0 and 90 degrees mostly. If you're walking in radians, they'll be somewhere between 0 and pi over 2, which is a weird range to think about. There's another way of measuring angles too, right? You could just say, what percentage of a full revolution is this angle? This is less often used, but let's talk about that too. Yeah. So let's think about, let's compute this. Let's figure out how to convert from radians to full revolutions by thinking about one full revolution. So let's figure out the radian measure of a full revolution by doing exactly that. So let's think about a full revolution. There we go. I've walked all the way around the circle, and you already told me what the circumference of a circle is. So what's the, let's make this radius higher. What's the circumference of that circle? Well, you told me that like seconds ago, right? 2 times pi times the radius, or pi times the diameter, but the diameter is not given here. So the radian measure of this angle should be arc length divided by radius. What's arc length divided by radius here? Just 2 pi. It'll be 2 pi radius divided by radius. Oh, that's just 2 pi. And that's the radian measure of this angle. So here's the payoff. One full revolution is the same thing as 2 pi radians, where pi is around 3.14-ish, so that's like 6.18-ish. Cool. Folks feel all right? So this gives us a conversion factor. We can convert now from radians to full revolutions, or from full revolutions to radians, by multiplying or dividing by 2 pi as appropriate. Could we do the same thing to convert to degrees? Yeah, so let's get a conversion factor from radians to degrees. This will be a useful conversion factor to know, because sometimes you'll want to walk in one but be given information in the other. So let's do that. How many degrees is one full revolution? 360. That's how degrees are defined. One full revolution is broken up into 360 equal pieces. And we know that that's the same thing as 2 pi radians. So whenever you see things in one unit you want to convert to another unit, you just need some conversion factors. So let's walk with that. A d degree angle is the same as d degrees. And let's multiply by 1. So if the thing on the bottom is equal to 1 revolution, then I've multiplied by 1. How many degrees makes one full revolution? 360. I get that it's literally just like right there. So notice if we multiply these together, we'll have degrees divided by degrees. That'll convert us to full revolutions. How many radians to a full revolution? Oh, neato. So that means this is also equal to 1, this fraction. And multiplying by 1 doesn't change a thing. Full revolutions cancel, so what are you left with? d times 2 pi over 360, and now I'll specify that it's in radians. Let's simplify that some, because this is a formula we'll use an awful lot. Do you see any common factors you can cancel? 2, right? 360 is 2 times 180. So here's the conversion factor. D degrees is the same thing as pi over 180 times d radians. If you want to convert from degrees to radians, multiply by pi and divide by 180. That feel pretty good? So maybe we'll even blow by this justification. So if you go from degrees to radians, you multiply by pi over 180. That means that if you want to go from radians to degrees, you should do the opposite of multiplying by that. So what should you multiply by if you go from radians to degrees? Yeah, 180 over pi. And let's just do some quick conversions. What's the radian measure of a 30-degree angle? So to do that, you take that 30 degrees. I'd like to convert 2 radians. So I think here is the conversion that I want to use. 30 degrees times pi radians over 180 degrees. And in some sense, there's a final answer, but we should probably simplify that a little bit. I guess one thing we can do for free is the degrees will cancel. The 10 and the 30 will cancel with the 10 and the 18. Is 18 a multiple of 3? Yeah, 18 is 3 times 6. So in the end, we just get pi over 6. And it is in radians. That feel pretty all right? So we've already done 3. We found that an angle measure of 90 degrees is a right angle, which is pi over 2 radians. But let's do that one. And I think I want to have you do it. An angle of pi over 5 radians. Convert that to degrees. Once you have an answer, check it with someone else around you. Once you feel confident, let me know what you get. I hear a 36 degrees. People agree? Cool. Should I talk through the computation? Okay, then I will. So pi over 4 radians. I want to convert from radians to degrees. It looks like there's the conversion factor that I need to use. So pi over 4 radians is equal to 180 times 180 degrees divided by pi radians. So far, so good? And maybe before we use a calculator, let's cancel the things we can. One thing that should cancel is the radians. I want an answer in degrees, so those should cancel. Is there anything common between the numerator and denominator? But the pi for sure. So I have 180 over 4. Let's see, 180 is 90 times 2. God damn it. Thank you for saving me before I went too much further. So I have 180 divided by 5. Is 5 a factor of 180? Yeah, because 180 is a multiple of 10. I guess you have to do some more to figure out that it's 36, but you've already told me that it's 36. Groovy. That seemed pretty all right. Nice. Maybe let's play one last game. There's an angle of 1 radian on the previous page. let's try to convert 1 radian into degrees. So if you want to convert that into degrees, what do you need to do? What do you multiply by to convert from radians to degrees? 180 over pi, because that'll be 180 degrees divided by pi radians. Oh, cool. So the radians cancel. Multiplying by 1 doesn't do anything. Put a double slash to indicate that that's different from the cancellation. And if you want to know what 180 over pi is, well, I guess it should be about 180 over 3. But if you want a better approximation than that, well, you know how to get approximations. 180 over pi is about 57.3 degrees. Cool. That seem all right? And maybe we'll even see if that seems intuitively correct. I claimed that that angle was 1 radian, right? That look about like a 36 degree angle-ish? That seems reasonable. Sorry, 57 degree. All right. So, what are some other things you can do with angles? So there are 2 things left in this packet that I want to hit. I want to measure areas of sectors. So what is a sector? A sector is some region that looks like that, where you start at the center of a circle, you draw out 2 lines, those 2 lines cut out a little chunk of the circle. Let's figure out its area. The other thing that I want to do is I want to talk about the conversion between angular and linear velocity. So suppose you're a little bug standing on a wheel that's spinning around. That wheel has some angular velocity. It's spinning around some number of degrees per second. Yeah. It's spinning around at some number of degrees per second. That bug is now traveling at some speed. It's traveling some number of feet per second. How do you convert between those 2? Those are the 2 topics that are left to hit. Let's hit those 2 topics. So first, sector area. So, here's, I won't justify it, I will state a theorem. So suppose you start with the circle with a radius center, and you draw a sector of angle theta. Then the area of that sector will be, let's try to walk it out in fact. What's the area of a full circle? And that should correspond to how big an angle in radians. How many radians is a full circle? 2 pi. So when you have 2 pi radians, you wind up with pi r squared as the area. Well, that should mean somehow that like every 1 radian should result in r squared over 2 area. So the general conversion, and we'll check this in a moment, the general formula for the area of a sector is area is equal to r squared theta divided by 2. And let's just check that that's right by plugging in a few sample values. What if you rotate by an angle of 0 radians? How big should that area be? Yeah, nothing. You start with a line and you draw the exact same line. There's no area between them. What if so theta equals 0 should give an area of 0. Does this formula give you 0 when theta is 0? Yeah. We've already have this. When theta is 2 pi, the area is r squared theta over 2. When theta is 2 pi, it should give you pi r squared. Plug in theta equal to 2 pi. Does that give you pi r squared? Yeah. So I think this formula works. Nice. And maybe here's a caution. Do you think you'll get the same formula if you measure things in degrees instead? Oh, you'll get a formula. It will be an inherently uglier formula. So here's the philosophy that I'll suggest. If someone gives you an angle in degrees, convert it to radians. Then compute the area. So let's just see some examples. Because that's a really simple looking formula. It would be really a shame if there were an extra 180 over pi sitting there. So let's compute the area of a sector whose angle is pi over 3 and radius is 4. And this is the simplest thing possible, right? What's the formula for the area? It would be r squared theta over 2. What's the radius of the circle? 4. So it'll be 4 squared times what's the angle? Yeah, pi over 3. And then I need to divide by 2 because there's a 2 there. Does that look like something super easy to compute? Yeah, what is it? I think that I want an exact value as well as a decimal approximation. Right here, an 8 pi over 3. That agree? And how many people got a decimal approximation for that? What'd you get? Cool. I think I remembered enough that the 7 should round up if I round there. Groovy. So let's do it in degrees, though. Let's compute the sector of an area of angle 30 degrees and radius 4. So I guess first things first, let's convert that 30-degree angle into radians. What do you multiply by to get degrees into radians? Times pi, because it's pi radians divided by 180 degrees. The degrees cancel. So you wind up with 30 divided by 180. Oh, hey, did we get that to be pi over 6 just moments ago? Okay, cool. So now that we know theta, can we just use this formula? So the area is r squared theta over 2 is 4 squared times pi over 6 divided by 2. And, well, maybe I'll even try to do it without doing the hard walk again. Is this angle exactly half of the angle above? So will the area be exactly half of the area above? Yeah. Because that's this divided by 2. Folks feel all right? Nice. So there's the formula for the area of a sector. Let's talk about spinning wheels and angular velocity. So you have some circular object, maybe it's a wheel or a gear or something, spinning about an axis centered in its center. The angular speed of this thing is given by, well, it's some number of measured in radians per second will be the number of radians that this thing spins around per second that the thing goes. Just how many radians does it trace out? The linear speed, let's write that a different way. How many radians does the angle trace out in a second? The linear speed is just how far does a point on the circle, say that point, travel in a second. That seem like a reasonable set of definitions? And maybe here's the bigger point. I will often use the Greek letter omega, lowercase omega, to indicate the angular velocity. I will use the Latin letter v to indicate speed. These things are now related by linear speed is equal to the radius times the angular speed, as long as you're measuring everything in radians. Do you think, well, if that works in radians, do you think you could also do something like this in degrees? Yeah, you'd be off by a factor of 180 over pi, so your formula would just always be uglier. This is what's nice about radians. Radians are defined using geometry, so if you're doing something geometric, the formulas will all be nicer if you walk in radians. So let's walk a few examples. So let's suppose you have a gear of radius 5 inches, and I'll maybe put this down. Velocity is equal to r times omega, spinning at 6 revolutions per second. Let's try to compute the linear speed of this gear. So I guess the first things first then. We want to go from angular velocity to linear velocity. That formula does that job, right? But is our angular velocity measured in radians yet? No, it's given in revolutions per minute. How many radians is it per full revolution? 2 pi. So 1 full revolution is 2 pi radians. That means 6 revolutions per minute is 6 times 2 pi radians per minute, also known as 12 pi radians per minute. Oh, nice. Does that tell me what omega is in angle, in radians now? Yeah, so there's my choice of omega. Does the problem tell me what the radius is? Yeah, if I want the linear speed, I should multiply those two things together. So 12 pi, and maybe I'll put some things here, radians per minute, times radius 5 inches. And so this is where like the unitless feature of radians will come into play. So that looks like it should expand out to like 60 pi inches times radians per minute. Which is weird. I expect to just have unit of distance per minute because this is speed. This is linear speed. Radians are a unitless thing. Radians just tell you what is the ratio of radius to arc length. So whenever you see a distance next to the radians will just go away. It'll tell you that it's going from something involving a radius, which it is, right? That the inches there came from a radius. It's telling you that it's converting into something involving the arc length, which it is. It's now a point traveling along the arc, along the boundary. Whoop. So, let's do, what trouble is with like 20 seconds, I don't think I can do another example. So I think instead of going over, which I know is usually my habit, making up some excuse that, oh, I'm not actually over time yet, this time I'll stop on time. So, what I'll encourage you to do is think about this last couple of examples. In particular, this one, in which you'll convert from angular speed of one gear to angular speed of another. There will be a few steps. Think about that, and if there's demand, we'll talk about it at the start of class on Thursday. Yeah, so what do you think the linear speed should mean? I guess.
the distance traveled, not like an actual distance, not in radius.
Yeah, it's the distance. A point is the edge of the soccer ball. It's in 1 second.
The distance any point of the circle travels.
Yep. As long as you're measuring in seconds. Is this measuring in seconds? Okay. Yeah.
Okay, so for this one, I can't seem to figure out these two. I don't know if it wants like a decimal or...
Yeah. Let me turn that off. Show me what you've done.
So I kind of just put them into my calculator and I got like the positive and negative, and it didn't work. So I didn't really know what else to do besides like...
What did you plug into your calculator?
Just like the little equation, like this one right here.
So, right, the equation is 2 to the x to the 2
Yeah.
equals 12.
But did you put it into like log?
Yeah. What do you get when you put it in log form?
I don't remember which one was where.
So this is the base.
So log base 2 of 12 equals
Yep.
Economics class I did. I took 180 up there. So you cancel class on Friday.
So do you have to just like keep the square root of each side? Or like...
That seems reasonable. Is that what you did?
I honestly don't remember. I just remember whatever I put in was wrong.
Okay. So there's one thing missing. What happens when you get rid of a square root by square rooting?
Plus or minus.
So I think there would be a plus or minus. And let's think about whether the plus or minus is reasonable. And let's even just think about the minus. Is it reasonable to plug a minus in up here? Well, let's just start with the negative. Can you square a negative number?
No. You can?
Yeah. Well, what's negative 1 squared?
Oh, yeah. But you can't put it under square root, can you?
Yeah, but I'm not.
Okay.
There's no square roots in the original expression.
Okay.
So you're taking... So I think plus or minus are both valid choices. Do you know how to tell WebWalk that?
You just put it in plus and minus, right? So you just do like the minus and then comma.
And then the positive one, yeah.
Yeah.
WebWalk doesn't know about log base 2.
Yeah.
So it'll be log of 12 divided by log of 2. Log of 12 divided by
By
log
log of 2? Okay,
Yeah.
perfect.
Yeah.
Thank you.
And then just make sure that everything you want to be under the square root is under the square root.
Okay, thank you.
Yeah, I just have a question for you. This is one of the open-ended numbers. Is it okay if I went from this to just getting an approximation for it? Because like that's what you need is the approximation. I just want to make sure I didn't need to simplify this anymore.
I'd add some parentheses.
Okay.
So what do you actually mean to be in the denominator?
This piece down here, 1 minus that.
So order of operations, you would say first you do division, so
Yeah.
you do 7 over 1, and then subtract
Okay,
that.
so just put parentheses around that and then it's good.
Yeah.
Okay, thank you.
The format is good. I mean, I didn't read any of the other stuff, so I don't know if there's any other errors, and I don't know the answer to the question off the top of my head. In fact,
I checked it, like I put it back in here and I did get 30. So
good. I would even say that's something
I
that
just
I know what it means
wrote
to.
it like that to put into my calculator. Because
okay.
it doesn't,
Yeah.
I can't do like log base 2 of 3, so.
What calculator do you have?
I have the TI-84.
I bet it can.
Okay, I don't know how, so I just did it this way.
If you want to, then look up the manual for the TI-84 at some point, or your solution, your dividing by works just fine.
Okay.
I think the TI-84.
Okay, thank you.
Yeah. Oh.